Hey everyone, this is Max and Mankirat from Tandem. To those who don't know, Tandem is a fully open source cluster orchestration software meant for running inference on heterogeneous hardware on any sort of combination of clouds, whether that's on-prem, VPC. The core of the algorithm, the core of the company, I should say, is this algorithm we call COI. It's basically the thing that determines how do you actually place jobs and allocate resources accordingly. We published the algorithm as a white paper. It's fully open source, but today we thought it would be a good idea to kind of do a long-form whiteboarding session explaining end-to-end what the algorithm is designed to do and how it works on a very deep technical level. So this is going to be a long-form kind of lecture style. We're going to be here at the whiteboard, and Mankirat is going to walk through the algorithm, and then we'll just chime in with questions and explanations as we go. So without further ado, I handed it off to Mankirat.
Thanks, Max. We want to draw out the problem we're trying to solve at Tandem, this dynamic cluster management. And I think a good example would be at a large enterprise who's handling a lot of mixture of GPUs from on-prem to VPC, from multi-region, multi-cloud, trying to do many jobs all at the same time. It's very important to get the most out of your compute with high utilization and lowest dollar per token. Let's just lay out a small graph. For example, enterprise A has 3 jobs that they want to run at a certain time. Job A, B, and C. These jobs can be of different types. There can be online jobs. There can be batch jobs. Online jobs care more about latency, care more about tokens per second, but they care a little bit less about total throughput or total dollar per token. Whereas batch jobs really care about throughput maximization more than latency and care about the dollar per token as well. You get the whole nightly job done in the least amount of time possible. These jobs are also need to be deployed on a different set of hardware. And for this example, we're going to use 3 types of hardware resources that we have. Let's say we have an on-prem resource. We have Amazon AWS, and we have GCP. Within these resources, I can have reserved capacity between all of them. Especially in a VPC, I can also go for on-demand, and I can also go for spots. And same for both. Most of the times, enterprises these days just go for reserves because it's too hard to even deploy and fill over your price and your jobs on-demand and slots. But within these resources, I not only have NVIDIA GPUs, but I have AMD GPUs. In AWS, I have their latest Trainium or Inferentium GPUs. And on GCP, I have their TPUs. Currently, in the state of deploying AI, most people go with VLLM or SGLang. They want to deploy with Kubernetes on a single cloud. Maybe they use Ray on top of Kubernetes for distributed execution. But there's no way to deploy all of these jobs really on all of the hardware where the hardware is fragmented and get the most out of the utilization. Find the best fit for a single job for all the jobs in the cluster.
I think so on that, let's just stop for a second, because you mentioned VLM, you mentioned SGLang, all these things. I think to put into the scope of how large the optimization problem really is, let's outline the options that a person has at every level of the stack, and then basically the combinations you can make. You talked about hardware, but how do certain serving engines pair with hardware? Is a company using only NVIDIA chips with only VLLM? How do they make the choice of even what do you use?
So as a logical person, I will lay out the whole diagram as a normal person would try to go out. So if we go on this section real quick here, let's start from the outcomes and let's think back to what decisions we can make to get those outcomes.
Yeah.
Right. Couple things I mentioned. I care about TTSD. I care about TPOT, which is time per output token.
Okay.
I care about my tokens per second. I care about my dollar per token. I also care about my SL margin, how much room I'm leaving up. And then I also have some notation of priority or fairness. Right. These are the business objectives And in our case, let's label and categorize them into our y's. Okay? In the very beginning of what we can even do, let's categorize them as x. I want to divide this x in a subset of groups. Let's call them workloads. What is a workload? Workload can be different model types. Each model has different number of parameters. It has different KV head to attention head ratio, etc., etc. We have around 20 to 30 of these workload types. Within the workload types, I also have my input length, my average, mean, median input length, average, mean, median output length. I also have the pattern the traffic arrives on. I have how bursty is this? Online chats are going to be more bursty in nature than batch jobs. I have around 10 to 20 of these. Then I have actual physical characteristics, which is, okay, I have a H100. What is my memory bandwidth? What is my number of teraflops or flops? What generation of CUDA does this even GPU support? What attention backend can this GPU support? I again have around 20 to 30 of them. And then eventually I have some parameters that I can change myself, which will influence the placement of these workloads onto these physics. Let's call them knobs. These knobs can be, hey, do I want to do prefill, decode disaggregation? Do I want to do different types of parallelism, like tensor parallelism, pipeline parallelism, expert parallelism, data parallelism, and I can just keep on going all the way to context parallelism, et cetera, et cetera.
By parallelism, you mean like how I actually split the model on different GPUs to
Right.
actually run the inference.
How is the workload being split on the different GPUs?
Gotcha. So this is something that the people deploying the models
Can
would
pick.
have to provide themselves.
Right.
Okay.
We can pick if I want my topology to be prefix aware, if I want to do KV caching, et cetera, et cetera. I have around, again, maybe 10 to 20 of them as of now.
Okay.
Okay. Well, to kind of think about a story or a causal structure on how laying out these workloads on these hardware characteristics by the things I can change will influence my TTFT, TPOD, token per second, etc. To help us think about that, I'll consider an intermediary variable. In the intermediary variable, I can think about things like SM utilization. The more GPU I use, the less GPUs I have to use to get my job done, the more cheaper my dollar per token would be, right? What is my time on network? So I can say, okay, time on PP, which is pipeline parallelism. So pipeline parallelism leaves pipeline bubbles. The more time I spend on them, the higher my latency would be, right? What is my memory bandwidth utilization? What is my KV pressure? And around 40 of these intermediary variables directly on the hardware, which will tell me and highly influence my outcomes, right? So for a person to think about this, hey, how many workloads to put on how many physical characteristics with all the things I can change, which will all individually or in combination of each other change some of my intermediary variables, then will reflect onto my y's. The search space of doing that is in hundreds of millions. No person can dynamically do this, right? And in a lot of the enterprises, when we're talking about finding the best placement, it's not for one job. There's many jobs. Some jobs are coming in, some jobs are going out. Different jobs have different requirements even. So how do I think about from a jobs perspective? And then I have to do a joint optimization on how that job would interact with the hardware or the whole cluster is my whole goal.
Well, okay, so let me push back against that. If I'm just like starting to deploy these models and say I want to deploy an online chatbot, right, for my company. So perhaps I care about time to first token, right, because I want my users to have short latency. Why is the search space in the millions? I mean, like, can't I have most of these variables fixed to some like value and then tweak something that will directly affect TTFT? Like, why is it in the millions?
And if you're just going for one job, even if you think from a homogeneous cluster standpoint, we have a variable here which is on-demand spots. I can totally at times, at the very minimum, even if I'm meeting my TTFE at all times, I can still gain by decreasing my dollar per token, by increasing my utilization. There's always gains to be made. And also fixing this initially will take you weeks and weeks on end of exploration and doing it right. And then the search space, even for one of them, is in millions. Right? So manually doing this is hard. A lot of the research papers from a while ago, from last year, are trying to fit a mathematical model on this, going through every single combination possible, which they cannot. So the search matrix is still very sparse, and finding out what the ideal things would be. Right? A bigger problem is, since I have a magnitude of these jobs, I have A, B, and C. I don't want to just find a place. So let's come up with example placements, right? An example placement would be, okay, I have 8 replicas, which is my DP here, 4x H100, for example, and this could be TP4. Doesn't matter, right? Well, if I only have so much H100s and all of them are online jobs, if I try to hyper optimize, I might just give all the H100s to one job or to the other, which might starve out the other job.
Sure. Okay.
And I want to make sure that I think from a joint cluster standpoint. Right. So I want to make an algorithm, a system that will think from the cluster standpoint and not greedily for one specific job. Right. So I'm going to introduce 2 concepts before we move into how we can think about solving this problem. One concept I want to introduce is the concept of an edge. Another concept is the concept of a mechanism. So we talked about making a causal story, right? For edge, I want to think about a connection from an X to a V or a V to a Y. Okay, what is my connection between PP and pipeline bubble pressure, right? I want to make sure if this connection is one invariant and always reliable on a variety of hardware.
What do you mean by invariant?
By invariant, I mean this connection should not only exist in AWS, not only in on-prem, but across a range of environments that I might deploy.
Gotcha.
For example, my environment could be, I have AWS, region US East 1, in some reserved capacity, and then H100s, right? This is one environment. I can totally have H100s in a GCP region. I want to make sure my edges are invariant across the environments. Gotcha. So I'll introduce the concept of an edge confidence. If my edge confidence is 100%, that means, okay, pipeline bubble will always lead to pipeline bubble,
Pipeline parallelism.
will always lead to pipeline bubble, which will always lead to some decrease in TTFE.
Sure.
Right, that's invariant. And there's many of these edges. A mechanism, however, is a combination of these edges. It is edge x1, x2 going to v1, v2, going to some y, mean something in a scope. What does a scope mean? Think about our mechanisms as a playbook, right? Hey, if I want to do a chatbot, which is 13 billion parameters model, and 100 people are going to ping it every second, maybe I should never do pipeline parallelism. Maybe I should structure it on a specific type of GPUs in a specific manner. So I want to have this massive rule book, which is append only, and I can keep on learning new rules of inference. And if I can make this massive encyclopedia, then at every time, for every single scope, I can think about which combination of workloads and physics leads to what I want eventually. Right? So our goal is to make this massive rule book and initialize them with some confidences to think about what it means to do inference. What is the story of inference? Right? Okay, so we introduced the concept of edge and mechanism. Now, what do I consider a good placement? Is 8x H100 for chatbot 13B a good placement? How do I quantify that? Well, to quantify it, I'm gonna have a job score. Okay. What should a job score mathematically entail to make this happen? Well, I already talked about a known rule book. So if my job score is always meeting my target, well, then that's a good thing, right? So I will call it J. I will explain what J means. J is from my prediction of how the thing should occur on a cluster. Did it actually occur that way? Right? How far was I? Or how far was I from perfect? Before talking about any assumption, the whole mechanism, the whole methodology we're going to deploy relies on one assumption. So we're going to call it core assumption. I'll lay it out in blue here. So our core assumption,
Erase this as we go.
one, is that for every single time I make a decision, I pick a decision. So from n number of decisions, at least, at the very minimum, one of those decisions is within some epsilon error away from the most optimal decision, or most optimal placement. If you look at it from a graph, you draw this graph. Let's say this line here is my most optimal placement in the mathematical world. I want to be within some epsilon error away from picking a decision that's within this line, right? And to make the whole algorithm, I want to make sure over time my error decreases. I'm always making decisions within this error. My number of n decisions also decrease, so I'm not searching for a whole while. And ideally, I converge at the very end to always making optimal decisions. Right? So that's our
Question.
yeah.
What is optimal in this scope?
Optimal depends on what the user has deemed to be what is required by the user. If for the user, dollar per token matters the most, then the optimal decision is a placement on the GPUs, which are always going to be the cheapest.
So is optimal the hardware placement, or is optimal like the business outcome? Like
Optimal is the business outcome, which is dependent on the hardware placement. And for some people, latency matters the most, so my optimal decision is something that maxes out the latency. Okay? Well, one more representation I want to give, and why this is so hard, is we usually see a lot of these Pareto frontier graphs, right? For example, this is my token per second per GPU. This is my token per second per user. Right? And most people will draw something like this, where if I really care about per user token per second or per request token per second, my per GPU is going to be lower, and I want to usually find a place somewhere here. But that depends on what the minimum, so token per second per user is an inverse of my time per output token. So what is my minimum time per output token required? Right? This is one axis. Another axis people talk about is, so we'll call this token per second per GPU just normal throughput, just token per second. People care about token per second versus latency graphs, right? Based on my latency, so this something looks like this. If I have really low latency, then I'm going to produce less tokens. If I have high latency, I can produce more tokens, but I plateau out somewhere, right? And latency here is my TTFT, and token per second is my throughput. Right? Then there's another graphs which talk about dollar per token in combination with one of these, but I'm not dealing with a 2-axis dimension. I'm dealing with a 6-dimensional hyperplane. I want to make sure all the decisions I make, for example, ignore everything else. If I just want to make a decision between TTFT, TPOT, and token per second, my graph would look something like this, where I will lay this out, throughput, let's call it token per second per user, and let's call this latency. And I want to find the maximum of whatever hyperplane this is. Yeah. Right? The user has defined, hey, never be more than n number of seconds on the latency. So I always have to be less than this target. I always have to meet some token per second aggregate targets. So I need to be more than some teapot. And I need to find the highest throughput if it's a batch job for that. So I'm looking at a hyperplane here. If I add one more variable for dollar per token, I'm looking at another 4-dimensional hyperplane. And now think about a poll where I also care about fairness. Job A gets more priority than the job B. You can just keep on adding dimensions and want to do joint optimization over this hyperplane. Right? That's why the problem becomes a little bit harder.
I'm overwhelmed.
So my assumption here is I'll be able to find this maxima of a hyperplane. So another thing, I care about different things here. I want to minimize, so I'll call it min. I want to minimize TTFT. I want to minimize teapot. I also want to minimize dollar per token, right?
Yeah.
But I want to maximize throughput. I want to maximize my SLO margin. I want to maximize my fairness. So I'm dealing with two different scales. Okay. So to describe what J means here is I want to take a sign aware Chebyshev scalar. What does that mean? I want to know, okay, from my predicted outcome, let's say I have a model that predicts something, how far away was I from the most optimal decision? And if I can find that, the closer I am, the better my job score will be. The farther I am, the more improvement I have to go. Let's delete this a little bit. And I want to talk a little bit about what predictors are here. Okay, how can I get a notion of how well I will perform? Yeah. Over the years, people have, specifically by NVIDIA has released AIC, AI configurator, Tandemn. There's also LLM serving stack. Now LLMD has also made a serving simulator, which kind of helped me figure out, hey, for a number of workloads on a number of physical characteristics, what would my TTFT be? Or what would my dollar per token be? Time per throughput per second be, right? I can use some of these simulators as estimate. So let's just call it Tandemn. We specifically use these two in our algorithms as well. We also use another well-known simulator, which is past knowledge, right? I will have a performance database of all the past runs I've done. So let's say, okay, for our chatbot, Llama 3.270B, I got a number of V's and a number of Y's, right? And then all the way to some MOE model by GLM. For a completely different batch task, I got some V's and I got some Y's. Somewhere in this very sparse performance database lies an answer to some new user requests and what their V's and Y's be.
Are you talking about V's and Y's? Do you mean the mechanisms that we record? Or
V's and Y's, I mean the actual number. Hey, my pipeline over pressure was 70%, or my TTFD was 2 seconds for a specific configuration on a specific set of hardware.
But if it's running, are we using the mechanisms as well in sort of like simulator, or does that come somewhere else?
We don't use the mechanism in simulator per se. Okay. I will draw out how the algorithm plays out, but I use this specifically for the sake of simulation. For me to know if I deploy a certain setting, what would my outcome look like?
Right, because the mechanisms are just the relations,
right?
Not the actual. Yeah. Gotcha.
And we'll use our best friend, nearest neighbor algorithm to find out what a specific simulation would look like. And this, in combination, would make my simulator. So given a plan here is, okay, for job A, H100s, for job B, A100s, et cetera, in different configurations, what would my simulated Y's and B's would look like? Like I said, different people care about different things. So a common characteristic example you can take is if I were to weight everything, assign linear weights to everything. For online jobs, I really care about TTFT, so maybe 0.3, 0.3 to teapot, and everything else, I would be like 0.1, 0.1, et cetera, to fill it up for online. These are my weights. And for batched, it'd be the inverse of this, for example. Right? And I want to know, okay, am I meeting my V's and Y's for this specific set? So when I talk about J is a weighted augmentation of my Y hat. Y hat is simulated Y's, simulated outcomes, minus the ideal Z star. Z star is the best TTFT I've ever seen in my life for that scope. The best dollar token I've seen in my life. How far was my simulated experience from this Z star? Okay. And I want to normalize this with some ranges. And please read the white paper to get to know a little bit more. But this is my exploitation score. Right? If I have a good story about what's worked in the past, how close am I? I have a score for this job, right? But as we said, we have millions and millions of combinations. Even my performance database is going to be very sparse, right? I want to still explore. I want to give incentives. Like we talked about mechanism confidences. If some mechanism has a confidence of 0.5, that means this mechanism is not explored very much, right? I don't know how good this mechanism is. It's not been tested that many times, maybe. So I want to have an exploration term. So we'll talk about these terms individually as well. But logically thinking about a job score, I want to do what's already been done. I want to explore new options. I want to heavily demote the risk factor. And we'll talk about how we simulate and describe risk. And I also don't want my algorithm to go all over the place and just keep on switching. So I want to have a small switch cost penalty. And the switch cost can be low. I'm launching more chains, I'm wasting money, maybe I'm spending time in a cold start, etc. So I will think about a job score as knowing what's already been done, doing some exploration, minus the risk, minus the switch cost. This is still very greedy though. Right. This is only per job.
So this is the job score for an individual.
For an individual job. I want to make sure my job score is high for the whole cluster.
For all the jobs.
For all the jobs in the cluster. Because I want to find a placement for a job for all jobs in the cluster. Sure. So I'm just going to sum the job for all jobs. Sum this for all jobs. To get an aggregate score. To a cluster score.
Job. Yeah.
So I can convert this into a cluster score by just addition. And at each time I make a decision, if my cluster score is the highest, I might pick that job. Right? Okay, we talked about this, but let's walk through how I can even implement something like this in real life. How have we done it?
Do we want to clear up space on the whiteboard?
Yeah, we can probably get rid of our causal graph. We'll get rid of our simulator. And we can get rid of our mechanisms. And now, how do I make sure my assumption actually comes out to be true? How do I make a decision that will lead me to something with an outcome? I'll talk about a basic for loop we can do. Let's give this for loop 7 stages, and we'll describe those stages. And for now, we'll say that my for loops runs every 5 minutes on the cluster. This is the main cluster control that will run every 5 minutes on the cluster, produce a plan, run a plan, and actually deploy it on the cluster. Right? So let's talk about what my for loop consists of. For example, there's a couple of jobs that can happen. There's going to be active jobs, right? There's going to be pending jobs on the cluster. I'm given some resource map, RT, at the time t. And I want to make decision for those active and pending jobs. If I want to switch them, if I want to keep them, how do we place them on the resource map, correct? Sure. I will take care of this as an input at S1. S0, I will keep as start of my tick, to start all the processes. S7, I'll keep as end of my tick. S6, I'll keep as actually deploy. S5 as validate. S4, I actually want to produce a plan. So this is my reasoning, which will produce a plan PT at the time t.
Okay.
But I want to have a way to learn everything. Right. Let's say if I was at S4 already, I produced a good enough plan, I validated it, it got deployed. I'm not going to just produce another plan after that, right?
When you say plan, you mean allocating every job in that cluster to some sort of hardware for that job. Okay.
Doesn't have to be allocating every job. There's a couple of decisions we can make here. For each job that I have in a queue, I can either place it, or I can choose to defer it for next time. Maybe the timing is not right.
If the job is like a long running.
If a job is a weak SLO, I can choose to defer it. Okay. For any active job, I can either choose to do nothing, I can choose to evict it to place a higher priority job, or I can choose to swap its resources onto different resources. Well, when I've placed a job, we were talking about V's before. After I place a job, I get a very clear view of what the metrics are. What was the hardware utilization? What was the memory pressure? Right? How much CPF did I get? How was my teapot? Am I staying within my SLO? Am I destroying it, etc., etc. Right? So any simulator in the world, no matter who is it made by, is going to be off. And it's going to be even more off when I'm trying to do joint optimization over a group of jobs.
Why? Why would it be off?
Because real life physics, there's variables that we cannot control, like VLM version, right? Different inaccuracies and inefficiencies in the kernel level.
Even like the interconnect, right?
The interconnect level, et cetera, et cetera. So I'm always going to be a little bit off, right? But I want to make sure what I'm seeing is actually what's happening. So I want to collect metrics. And S2, I will take it as my cluster snapshot. I will collect metrics. And I will use these metrics to improve my assumptions about inference, right? We have a causal graph, we have a causal story, which initialization is empty, right? I don't have many proven points that, hey, this is how it's working. I came up with a plan. I know, hey, this might work, but I want to be sure about it, right? So I want to do a couple of things, and we'll keep metrics as my statistical tests, which we'll talk about, and I want to have it as an updation step. And I want to do some slow loop updates. I want to make more decisions. So this is the trajectory I will follow as a for loop, as a finite state machine, to actually place and do all jobs in a cluster. We've been talking about placing a job and thinking about what a job means. All of this job score is happening at S4. Okay. So let's zoom into S4 first, and we will come back and talk about all the other parts. Okay. Right. My S4 design is actually an LLM agent. It's a, and I can do this option, yeah. It's a LLM agent, so we'll talk about S4 here. This LLM agent is a long-running agent. It has full context of prior history, prior metrics, prior evidences, and the playbook. It's running in a root and substyle, which means the root will always make joint optimizations. So let's coming back to the plan, A, B, and C. It will always think about the same cluster. It will allocate some resources to leaves, which within the allocated budget for the hardware, actual hardware, can produce a plan and produce TP, PP, DP, different types of parallelism skills. We would loop it back, and we would produce a plan. We can also launch multiple trajectories of this LLM. And that will be my n number of decisions. I want to make sure within n number of these decisions, either over time or multiple trajectories, at least one of the decisions, which scored the highest, in our case, is within some epsilon error away from the most optimal decision. Okay? We've been seeing a lot of research coming out of UC Berkeley, coming out of all the labs in this world, talking about evolutionary algorithms that improve themselves over time, find better solutions. Even in systems research, ADRS has published EvoX, Evolve, all these algorithms that will find a better solution of doing a certain task. So this is a scoped down evolutionary algorithm to find the best cluster placement at all times. Right? So, and the S4 will then utilize a bunch of, so of course, we're not going to make LLM make decisions like go launch 1,000 H100s and go crazy. We're going to harness it really heavily. It's working in a strict trajectory, and it has to use our tools that we give it. One of the major tools is looking at how many resources you have, looking at all the active jobs, pending jobs, but also scoring everything properly. And then we make sure we heavily validate that the algorithm, whatever the tools is predicted, is not going to blow up any ceilings and floors, et cetera, et cetera.
So a lot of the people that I feel are trying to tackle this, and even like some of the people we've spoken to, feel like an LLM just on its own. Like, you know, we have Fable 5 now, right?
Yeah.
Why can't I just like, you know, we're using an LLM at the core.
Yeah.
Why can't I just like slam all this context into Fable and have it give me some sort of answer? Like, how is this different? Like, what is the tooling around it that guardrails the suggestion?
I think the most important thing is the data that we collect, our performance database. LLMs are really bad at predicting performance of what one model performance would be on a GPU. So we need a lot of data so it's a data-driven search that we're going to be doing. Plus, LLMs also cannot just reason over a million traces like that if it's not scoped down. So with all the things that we do with our mechanisms, our rulebook, we've reduced the search space heavily. And then we let LLM, the reason why we're using LLM is not to be just for the sake of our use agentic. LLM has crucial domain knowledge that will allow us, hey, in this, okay, PP leads to this, which leads to that, so maybe I shouldn't do it, or maybe I should do it, right? It can reason over a bunch of metrics and give out a reasonable plan. And it's not just free-flowing on its own. It's not like, hey, type something in hot code, get it right. It's very heavily harnessed, and we'll use all these scores. Okay. So S4 is an LLM loop. The input is all the jobs, resource map. The output is a given plan. And let's talk about the job score a little bit. We want to describe how this algorithm works after S4. We talked a bit about the exploit score. I want to talk a little bit about this explore score here. We talked about how we have confidence of mechanism and edges. What about when the confidence is 0.5? And when the number of visits on this mechanism has been low, right? That gives me an incentive to actually try out this new mechanism, to try out this new pairing in our causal structure. So we prepared for the edges and for the mechanisms a score where we look at the uncertainty of edges and uncertainty of mechanisms. And when uncertainty is high, I want to actually give an incentive to explore this unexplored mechanism because it might turn out to be good and favorable for my result. Right. Let's look at switch costs here a bit. What kind of switch cost can I have? I can have a cold start cost, which can eat up valuable time from my SLO, or just keep the GPU running and cost me more. I can have a general, hey, I'll launch a bunch of GPUs without killing the old GPUs, so I'm spending more time switching and migrating my requests over. So I want to minimize my switch cost. I want to give it a soft penalty and never go more than some switching cost budget. And I also want to have a budget for how many switches I'm allowed to make each tick. Right? I don't want to be switching up the whole deployment for A, B, and C. I want to have some sort of budget. And I want to make sure all these variables are actually adaptable. I can choose when to exploit more. I can choose when to explore more. When to increase the budget, decrease the budget, or decrease this penalty, right? And how can I do that? It's based on the state of my cluster. If my cluster is performing well, or what I like to call the regret that we have, right? So let's define what regret means. At each time I make a decision, there's a possibility I could have made a different decision that was better than the decision I make, right? So I want to classify all the decisions I make into quadrants. The way I want to make these quadrants is, my reasoning of the causal story actually matched with my outcome. Hey, whatever I thought would happen matched with what actually happened. So V's and Y's. Q1 is my mechanism was correct and my deployment resulted in a good way as well. Q4 is my way of thinking was wrong, my mechanism was also wrong. Q3 is, okay, way of thinking was wrong, but I did it correctly. And Q2 is the other way around, right? This is when I got lucky, and this is when I got unlucky. This is, Q1 is what I'm striving to be there, and Q4 is, okay, my confidence should decrease, right? So my regret is actually the number of times I land in Q1 versus the number of times I could have landed in Q1. Ideally, I should always be landing in Q1, right? I always want to make sure my reasoning, my causal story is complete, and based on those reasonings, I make the correct decisions. So regret is how far away am I from, so Q1 ideal minus Q1 that I actually did. Based on this regret, I want to tune how much I should be swapping. I want to tune how much I should explore, how much I should exploit. If my regret is very low, there's no reason for me to explore, really, because then I've already understood the story, I've understood the assignment, and I'm going to keep on doing it. Right? If my regret is high, then I want to give more incentive to explore. So I'm going to give a couple, so let's call the exploration incentive, which I'll call EIG, incentive to be beta. And these are just a couple of variables I can tune. And all that tuning happens in my updation steps. After I view the telemetry, after I know if what happened was actually what I perceived would happen, I would, based on all these metrics, update my variables, which would result in a more tweaked, more better, and updated job score later on. And this job score directly impacts the actual plan I release. Right? The most important.
How does, not to interrupt. So in this way, how does regret correspond to switch cost? Like, if you see that you have a pretty low switch cost, so you'll go, how does regret play into the two?
And I just want to mention, so we can talk a little bit more about regret. I don't actually care if my regret is high at a single point.
Okay.
I care more about how my regret slope is changing. I want to calculate a second derivative, so I want to calculate the rate of change of my regret.
Okay.
Right. I want to see if my regret is increasing or decreasing. If my regret is decreasing, I'm on the right trajectory, and I should keep doing the variables that I'm thinking about, right? Specifically in switch cost, regret is, if I have high regret of a mechanism and a high regret of a edge, then based on that, I should switch more. I should try to switch more and maybe try more options, try more of the mechanisms to maybe see if I will land in Q1 more often.
Okay.
If my regret is very low, then I shouldn't be switching at all, because switching is a penalty.
Right.
And if I switch too much, I will do things that I'm unsure about, and that will risk me even more in my penalty. Right? I think risk is the more core component of things I want to talk about. Over time, so I will delete some of this component about regret here. Over time, my simulator gave me a V hat and a Y hat. These are my predictions of what my throughput would be, of what my SM utilization would be, right? But I actually saw some actual, so all these V's and Y's are a list of variables. And I actually saw actual V's and actual Y's after I deployed it, right? Like we said, they're going to be different because no simulation is perfect. So there's going to be a residual between them. So I'll just call it residual R, which is V hat minus actual V. Right? If I can plot all these residuals on a histogram, etc., I will have a basic history of how my residuals are looking, right? How far away I am from this residual. And these residuals can be positive residuals, negative residuals, etc. Right? I want to make sure in my own head that I'm never gonna pick a placement, pick a TP, or parallelism configuration that's gonna place me outside of this risk, place me outside this residual. Because these are still known risk profiles, right? I'm off, yes, but it's over time I can create a histogram. On this residual, I can place an invisible radius, and we'll call it So the technique I'm going to use here is a well-known risk optimization technique, dynamic robust optimization, which will give me radius. And the distance I want to calculate, I don't want this to be just scalar distance. I want to calculate the Wasserstein distance, which is Earth's mover distance, which is going from this residual to a minimal residual. What changes do I need to do to go to that level, right? And my best residual ever, this band, assume that this band has a radius r. My radius r is 0, right? I'm very good on the risk side. So over time, the more I observe, this radius of risk, this DRO band, should decrease. And when it decreases, I will know that I'm converging. So I'm talking about scores a lot, and I'm talking about updations a lot. What is the reason why I'm doing these updates, right? And I'll talk about the 3 convergence criteria.
So again, like to scope this out, this is happening on a per job basis, but you're taking the summation of all the jobs to get a cluster-wide score.
Correct.
Okay.
So I want to have a general, even if all jobs are best on H100s, some job will miss out as SLO if I don't have that resource. Okay. So even if I have to give job B an L40 instead of H100, it's fine as long as it meets its targets, right? So my criteria to converge here is, in a long horizon, I will switch very less. So my switching budget will go lower. My incentive to explore will go lower because I've already known everything. Correct, because I've already known everything. Let's come back, we'll do it here. My DRO band will decrease significantly. My switch cost will decrease because I'm not going to be switching as much. And my Q1 rate, my regret, will come to 0. I will always be landing in Q1.
What was Q1 again?
Q1 is that my prediction of what I predicted actually went the way in real life.
Gotcha.
It actually happened.
Okay.
For that to happen, there's a core assumption that my simulation is also improving. My simulation needs to improve over time based on the real metrics.
Right.
So this algorithm not only gives me a better placement, but over time, if I keep on running it, it'll also give me a really good simulator at the end of the day.
Y hat is based off?
It's based on simulation. And I will learn what different placements do on different hardware.
Yeah.
So my simulation, my performance database increases.
Sorry, V hat and Y hat, I should say.
Yeah. So performance database increases.
Yeah.
And the bigger my performance database is, the more likely I am to make the best decision, my optimal decision, which is error is going to be 0 away from optimal. The more likely I am to make the optimal decision the first go. It's very hard, but over time, I will converge to there. Okay. So we've talked about some convergence criteria about the risk. At each time, I want to calculate and update these things in the slow update, and I will keep on repeating the loop. I can, of course, if some company wants to deploy it in-house for serving LLMs, they care about privacy, so they want to be serving this LLM agent also in-house. We've harnessed it in such a way that you can also use a much smaller LLM agent that can run on just a single machine. So you're not running a GLM 5.2 to run your Llama 70B models in production.
Yeah.
So we've harnessed it very heavily, so the performance is good. A couple of criteria we're looking for to evaluate this is my job admit rate decreases. My job admit rate, what I mean by that is I accept more jobs at time t based versus naive optimization, right? Around 10% more jobs accepted at time t. And my dollar per token also significantly decreases versus naive baselines of at least 30 to 50%. So those are the couple criteria alongside, okay, the time on queue should be less, I should be very fair, I should care about fairness, and the time of the job completion should also be less. But I think that completes the mathematics of it. And the rest is, we will collect a lot of data, a lot of these GPU metrics, and learn the way inferences should be. We will build out our causal DAG to high confidences. At the end of the day, I won't have many 0.5 confidences because I'll have explored and exhausted the graph of inference possible. So that covers the math. We discussed the reasoning steps, the validation steps. In this video, we talked a little bit about the math itself, the algorithm itself. The beauty of the algorithm is no matter if a new system architecture comes up, if a new GPU type comes up, which changes my X's and B's and Y's, I will always learn. Even if I add more vertices and nodes to my DAG, I will always learn and update that DAG and learn the confidence of it. So it's a very adaptive algorithm that can be applied to many things.
So where does this where would you see this shining? Because like a lot of the things you talked about in terms of acceleration, risk, switch costs, even job scores, it feels like very, especially when you consider the mechanisms, like very specific to a cluster, right? Like it's self-optimizing in the sense that it understands the kind of constraints in which it's running. Like, is that better for a company in terms of it learns the workloads and the placement for that company?
So it'll learn the workloads and it'll adapt to new workloads as well. But I think the most value anyone will see out of this would be when their GPUs are all over the place. They have, again, on-prem hybrided with different VPC, especially on heterogeneous hardware, is where the search space really blows up and goes out of control. And that's where people will benefit from it the most.
How does this, because like, you know, nowadays there's a new model, Kimi K3 just came out.
Yeah.
What does this help with day zero deployment? Like
It definitely does.
How does this adapt to new model architecture?
Even though it's a new model architecture, a lot of the things that we've learned from the past, from our playbook still apply, right? And it will definitely help in giving not the best placement, but a suboptimal placement initially to enable day zero development. This is sweet. Rather than just naive and go out and explore some TPU.
Yeah. Sweet. Yeah. Dude, awesome. Thank you. Thank you for the in-depth explanation. Yeah, thank you guys for watching. This was like almost an hour, right? The entire algorithm paper, if you want to read, instead of rewatching this 50 times, is on our website. We're going to link it somewhere in the description probably. But yeah, anything else you'd like to add?
Yeah, so we walked over the algorithm itself. I think next we should talk about the system that actually enables this algorithm to run in a multi-region, multi-cloud environment on a processor.
Awesome. Cool. Thanks, guys.
Thank you.